All right, guys. Hopefully you are doing all right tonight. We are going to be taking a look at the Unit 6 study guide. Um, Again, just as a reminder, I'm not going to necessarily go over every single problem. I will try to go over one of every single problem type. And we are going to take a look at the multiple choice section of the study guide as well, kind of at the very end. That is not for a grade, but will be very helpful going into our test tomorrow. So let's consider what we have going on here with I'm going to start at number 2 because in order to do number 2, we're going to need to, or rather, in order to do number 2, we need to be able to do number 1. We kind of will do it naturally. In this case, we are given the following triangle where we are told that this angle here, this is A, B, C, A, B, C. This angle here, 45 degrees. This angle here, 55 degrees. Missing this angle here, and we're told that A is equal to 6. And we are trying to find the rest of this information. We're trying to find B, trying to find C, we're trying to find angle C. First and foremost, probably the easiest thing to find here is the missing angle. So when I know 2 of my angles, the way we can find the third is obviously going to be subtracting from 180. So 45 plus 55 is 100, and 180 minus 100 will give us that this should be an 80-degree angle. And this is perfectly set up for our law of sines, mainly because we have a known angle to side pair. So if we know an angle and a side, then we can go ahead and set up our law of sines. We're missing only these side lengths here, so I'm going to set it up in this way. That's 6 over sine of 45 degrees is equal to B over sine of 55 degrees, and that's 6 over sine 45 degrees is equal to C over sine of 80 degrees. Solving for B, I get that B is equal to 6 times sine of 55 degrees over sine of 45 degrees, whereas C is going to be equal to, again, multiplying, solving for C, 6 times sine of 80 degrees over sine of 45 degrees, which you could plug into your calculator to figure out if we absolutely needed to. But in this case, this is how I would personally prefer you answer. All right, number 3, we run into something that is similar, but that is kind of slightly fundamentally different here. So in this case, we are given, again, another triangle. Not a right triangle, but did kind of turn out one, that's fine. So we're told that this here is 63 degrees, this angle B, this angle A, 5.5, and 4.7. Again, we run into the fact that we should be doing law of sines here, right? We know angle C as well as side C, and all we are missing is side length A and our 2 angles. In this case, because we will need to find the angles first, because most of the information that we're missing is angle information, we are going to need to find the angles first. And as such, I'm going to set it up slightly differently than how we did up here. In this case, this is going to be that sine of 63 degrees over 5.5 is equal to sine of B over 4.7 just makes solving for B a lot easier. Multiplying both sides by 4.7, I get that sine of B is equal to 4.7 times sine of 63 degrees over 5.5. Now here, we have 2 different possibilities. Either, whenever we're like solving and we get this like sine of B is equal to some kind of positive number, 2 possibilities. This could either be a quadrant 1 theta or a quadrant 2 angle. Both of those are possible. And so we need to account for both possibilities. The quadrant 1 is the easiest one to do. So this is going to be, sorry, we said 4.7 sine of 63 over 5.5. 0.7 sine of 63. Make sure you're in degrees for this, over 5.5. If you got an answer that feels a little bit strange, probably not. And then taking the inverse sine of this in order to get our quadrant 1 angle. This is going to be a 49.59 degree angle. So B here, our first option anyway for angle B, which I'm going to call angle B1, is equal to 49.59. If that is the case, then our first option for angle C is going to be 180 minus 63 degrees minus 49.59 degrees. That is going to give us sorry, this is about 113, no, 112. So 13. So this is going to be sorry, 67.41 degrees. Does that feel right? It's about 130 plus 50. Yeah, perfect. 67.41 degrees. And looking for, in this case, that missing side length of A. Sorry, I called this C. This is not C. This is our missing A here, A1 being equal to this. And so our missing side length A, we can find by doing A over sine of 67.41 degrees being equal to, and we'll use the one that we know, which is 5.5 over sine 63 degrees, which I believe works itself out to be about, well, we'll double check here. So 5.5 sine 67.41 degrees. I get that this is about 5.7. Call that A1, first option for A. Now the other thing that we have to consider is, well, maybe it's a quadrant 2 angle. Maybe it's the equivalent angle in quadrant 2 that is giving us this triangle. In order to find the equivalent, so my second option for angle B, we're simply going to take 180 minus my first option for angle B, which in this case was 49.59, which gives me 130.41 degrees. But what you'll notice is that this is too big. If we try to do 180 minus 130.41 minus 63, we are getting a negative number, and so this simply does not work. These are the only possibilities in this particular case. I don't know what that was. These are the only possibilities in this particular instance for our triangle. All right. And then lastly, let's take a look at number 4 here. So in this case, we've got, again, some kind of triangle here. Call this A, B, 37, 11, and 8. And this is C. Now, fundamentally different about this problem versus the ones that we've seen before is that law of sines is not going to be a particularly useful pick. In the examples that we've had before, we've known a side ratio pair, but here we don't know a C that goes with a C, or an A that goes with an A, or a B that goes with a B. We only know one of each, and so law of sines is not going to be particularly useful for us here. If law of sines doesn't work, though, we have instead what is law of cosines. In this case, that C squared is equal to A squared plus B squared minus 2AB times cosine of C, and solving for C by taking the square root of both sides. This is going to be, get my order right here, it doesn't matter, but I'll just be consistent. 8 squared plus 11 squared minus 2 times 8 times 11 times cosine of 37 degrees. Which, plug into your calculator. If you didn't have access to your calculator, that's obviously as far as you'd be able to go. But this is about 6.67, which is just from having done this earlier, right here. All right, let's start. So now the only thing that we are missing are our angles. And you'll notice that now we do actually have the ability to do law of sines, but it's going to be a little bit more like example 3, which is just a little bit trickier than example 2. And so rather than doing another law of sine setup, which you totally could do, and it would 100% work, but rather than doing something like that, where we're having to check to see, do we have 2 triangles, do we have 1 triangle, blah, 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 let's instead just set this up as, again, law of cosines with looking for angle A. So angle A, well, actually, sorry, our law of cosine setup while looking for angle A is that 8 squared should be equal to 11 squared plus 6.67 squared minus 2 times 11 times 6.67 times cosine of that missing angle A. Be very careful of PEMDAS in this case. I would say the same thing above as well. Be very careful of PEMDAS. It's the biggest thing that I see people mess up. We have to undo with subtraction first, and then we're going to divide while trying to isolate A. So this is 8 squared minus 11 squared minus 6.67 squared divided by negative 2 times 11 times 6.67, which is equal to cosine of A. And this right here, this is our cosine of A. And so taking the inverse cosine of this value to find that angle, I get that this is about a 46.27 degree angle. And since I know that ultimately my angles need to add up to 180 degrees, if we do 37 plus 46, we get 83.27. And so angle B should be 96.73. Because they all need to add up to 180. All right, let's take a look at number 7 here. So in this case, we are given the point 1/2 and root 3 over 2. And we are trying to convert this into our r comma theta form. Okay. So to find r, we know that this is the square root of x squared plus y squared. And then to find theta, we set up 2 equations. We say, what is cosine of theta equal to? What is sine of theta equal to? And then this is either going to be unit circle, or we're going to use some kind of inverse trig statement in order to represent our theta. In this case, I get the square root of 1/2 squared plus root 3 over 2 squared, which is the square root of 1/4 plus 3/4, which is just going to be 1. Dividing by 1, r might as well not be there, and so for cosine of theta, I get that this is 1/2, and for sine of theta, I get that this is root 3 over 2. This is a unit circle angle, so this theta, in this case, is going to be pi over 3. And so our point is the point 1 and pi over 3. Normally we'd be done here. If this were free response, you could just circle that and call it an answer. Unfortunately, what you'll notice is that for our multiple choice, that's not an option. We don't have that as an option. In fact, instead what we have is a series of angles that have to do with pi over 6, by pi over 3, sorry. So we get like 1 and 5 pi over 3, or -1 and 5 pi over 3, or 1 and -5 pi over 3, or where both are negative, -1, -5 pi over 3. The question is, which of these is equivalent to the one that we have here, right? Who's to say? Well, we're to say. We need to be able to figure this out. And so we need to figure out which of these points is actually a quadrant 1 point. So the way that we're going to do this, the way that we're going to figure this out, thing to note is that r being greater than 0 means we start right. R being less than 0 means we start left. Theta being greater than 0 means rotate counterclockwise, and theta being less than 0 means rotate clockwise. So in the case of 1 and 5 pi over 3, we are going to go over to 1, start to the right, and then in this case we are rotating by 5 pi over 3. That's a quadrant 4 angle, and generally the way we get to quadrant 4 is we pass through 1, 2, 3, and end, that's not what I wanted, pass through and end in quadrant 4. This point right here, about, is going to be, call this A, our point A. For -1 and 5 pi over 3, we're going to be starting here, starting to the left, right? And again, rotating counterclockwise, and we're going to pass through 1 quadrant, 2 quadrants, 3 quadrants, and stop a little bit into that 4th quadrant. This point right here would be our point B. So this point is Q4. This point apparently is Q2. Starting to the right, rotating counterclockwise. So starting here, rotating, passing through 1, 2, 3, and then stopping in 4. This here would be point C, which is the answer ultimately that we're looking for, but while we're here, we might as well finish. And for D, starting here, rotating counterclockwise, passing through 1, 2, 3, and then stopping right here. This would be D. Okay. So in this case, the quadrant 1 angle that we're ultimately looking for is, the quadrant 1 point rather that we're looking for is this particular value. All right, let's take a look at number 9. So this is r is equal to 5 times cosine of theta. Our goal here is very, very important. We need to know what it is we're trying to do because it's pretty different than anything else that we've really been looking at within the context of Unit 6. In this case, our goal is to replace all of the r's and all of the thetas with x's and y's. So for instance, I know that r is equal to the square root of x squared plus y squared. And I know that cosine of theta is equal to x. I'm getting a little bit ahead of myself, over r. And that sine of theta is equal to y over r. Now again, our goal is to replace all of the r's in terms of x and y, so I could also think of this cosine of theta as being x over the square root of x squared plus y squared, and I could think of this the sine of theta as being y over the square root of x squared plus y squared. That would certainly be acceptable. And if I think of it in that way, then this r could be replaced with what we see here, and replacing these r's too, and this cosine theta could be replaced with what we see here. In this case, I get that the square root of x squared plus y squared is equal to x over the square root of x squared plus y squared times 5x. And since I have no more r's and thetas, that can be my final answer. Number 10 is very similar, but kind of going in the opposite direction. In this case, trying to replace all of my x's and y's with things in terms of r's and thetas. That's generally going to be the easier direction because we know that x is equal to r times cosine of theta, and that y is equal to r times sine of theta. And so in this case, this will be 3r times cosine of theta plus 6r times sine of theta is equal to 1. Sometimes you would solve for r here. I do not need you to. That's great. We have no more x's and y's, just r's and thetas. Perfect. Okay, let's take a look at number 12 here. We are trying to write the following polar form complex number, in this case that z is equal to 8 cis of 4 pi over 3. Trying to write this in its rectangular form of a plus bi, which we can really think of as like x plus I times y, or a y times I, maybe is a better way to frame it in this case. And again, we just established that we know how to find x and y if we know r and theta. X, we said, is r cosine of theta. Y, we said, is r sine of theta. And so in this case, A should be equal to r times cosine of theta, and B should be equal to r times sine of theta, which in this case is given to us. This is 8 times cosine of 4 pi over 3, and this is 8 times sine of 4 pi over 3. This is unit circle. This is a quadrant 3 angle, so both x and y are negative, and in particular, pi over 3 reference, negative 1/2, negative root 3 over 2, multiplying them by 8, and I get my value for z. This is going to be negative 4, and negative 4 I root 3 for my y value. Not really the direction we focused on. But certainly we saw that in other contexts, particularly with like vectors and with our points that we could kind of move back and forth between the two. Mainly, though, we focused on the forward direction, which is what we see in number 13, or at least a part of what we see for number 13. In this case, we are told that z1 is equal to the square root of 2 minus I root 2, and that z2 is equal to 3 times cis of pi over 9. And we are trying to figure out what's going on with z2 divided by z1. Now for this, we're going to take advantage of the fact that multiplying and dividing complex numbers in their polar form is significantly easier than it would be in their rectangular forms. When we are dividing two complex numbers, this would be R2, we divide the R's, R2 over R1, times the CIS of theta 2 minus theta 1. And if we were multiplying them, like if we did Z2 times Z1, we would multiply the R's, R2 times R1, and add the thetas, theta 2 plus theta 1. Okay. In this case, though, we're dividing. Of course, in order to figure this out, we need to know what R2 and theta 2 is, and we need to know what R1 and theta 1 is. We already fortunately have R2 and theta 2, but we are missing R1 and theta 1. We don't know yet what those are, and so we need to find those values. R1 is going to be the square root of x squared, square root of 2, and then y squared, square root of 2, squared, plus, and this is negative here. I'll write this a little better. Plus negative square root of 2 squared. Positive and negative root 2 squared is just going to be 2 each. I get the square root of 4 here, which is 2. And my setups for sine and cosine, that cosine of theta is equal to positive root 2 over 2, and sine of theta is equal to negative root 2 over 2. This is then going to be in quadrant 4, and the theta in quadrant 4 that corresponds with these values is 7 pi over 4. And so a better way to write Z1 would be to say that this is 2 times CIS of 7 pi over 4, at the very least a better way, given what we have already. So in this case, Z1 divided by Z2, or sorry, Z2 divided by Z1 is R2 over R1, CIS of theta 2 minus theta 1. Now with this, we also had what was called de Moivre's theorem. I'm going to leave 14 as an exercise for the reader. We're going to look at de Moivre's theorem in the context of number 15. But 14 is obviously exactly the same as what we were about to do with 15. De Moivre's theorem states that if I have a polar form complex number, r CIS of theta, and I raise it to a power, this would be z to the n, then I can accomplish this by raising r to that power, and then CIS of multiplying theta by that power, which is just coming from a consequence of the fact that repeated multiplication of my r values, which is what we did when when multiplying two complex numbers, multiply the r's, add the thetas, that repeated multiplication turns into an exponent, that repeated addition turns into a coefficient. In this case, we are looking for the cube roots. What we can think of in terms of what that power is that this should be to the 1/3 power. We'll go ahead and say that n should be equal to 1/3. And then kind of a tricky thing here is that there should also be 3 solutions to this. Cube roots, 3 solutions. Now we have already found that Z1 was equal to 2 CIS of 7 pi over 4. And we could go ahead and apply de Moivre's here. The problem that we're going to run into is that that is only going to net us 1 solution. So what we need are other representations of Z1 that keep the XY information the same, but that change the R and theta information so that I can get different values for my cube root. And the way we can preserve the XY information while changing the r theta information, probably the easiest way is just to add 2 pi to our theta over and over and over again until we have a sufficient number of essentially starting points. This is plus 2 pi, which in this case we could think of as 8 pi over 4. That's how I'm doing this really quickly. So I'm just adding 8 pi over 4 over and over again. De Moivre's states that if I do z to the 1/3, then this is going to be 2 to the 1/3 times CIS of 1/3 times 7 pi over 4, which gives me 7 pi over 12. I'm going to get 2 to the 1/3, 1/3 CIS of 15 pi over 4 times 1/3, which is going to be 15 pi over 12, and 2 to the 1/3 CIS of 23 pi over 12. And again, we could do that with normal powers too. You would just use like whole number values of n, and you don't need to worry about the additional solutions unless you're looking at the roots. This is very, very specific. All right, all we have left are our vector questions. We are defining vector v, these are for all of the next questions, as 4i minus 3j, and vector w as 3i plus 5j. The first thing we're trying to find is v dot w. Now remember, the dot product is super, super, super specific. Like this is just, it's not hard to find. You just need to know how to find it. It's not going to give us a vector, so we're not going to have i's and j's anymore. This is just going to give us a scalar. It's just going to give us a number. And the way we find the dot product is we take the product of my x components, in this case 4 times 3, better, 4 times 3, and we add that with the product of my y components, in this case negative 3 times 5. This is 12 plus negative 15. I get a dot product of negative 3. Not hard, but if you don't know what a dot product is, obviously you wouldn't really be able to do this. All right, next, for number 17, we're asked to find the direction and magnitude of 2v minus w. For these, I like to just write out what these new vectors are, so I'm going to try and think of this as 2v plus negative w, just to make my life a little bit easier. 2v, in this case, is going to be 8i minus 6j, and negative w is going to be negative 3i minus 5j. Adding these two together, I get 5i, add the x's, and negative 11j. Now, we weren't asked to find this vector. We were asked to find the magnitude and direction of this vector. We should think of this as our x component, this as our y component, and the process is exactly the same thing that we've done up until this point. My magnitude, which is my r value, is the square root of 5 squared plus negative 11 squared, which is going to be the square root of 136. And my direction, which is my theta, we can get by doing our trig setups, in this case cosine of theta being equal to 5 over the square root of 136, and sine of theta being equal to negative 11 over the square root of 136. Now, these are clearly not unit circle angles. We should not know what these thetas are. And since these are not unit circle angles, what we need to do instead is construct the appropriate inverse trig statement. In this case, positive x, negative y tells me that this should be in quadrant 4, which tells me that I should use arc sine. And so for theta, I get the arc sine of negative 11 over the square root of 136. And finally, for number 18 here, we are asked for the unit vector of v minus w. Again, I like to think of this as always in terms of addition, so I'm going to think of this as v plus negative w just to make my life, I find it a little bit easier. If you wanted to do minus, that is, of course, totally fine. When I do this, I get I, and I get minus 8j. Yep. For my vector. Unit vector, so I'll call this v unit, is the normal vector divided by its magnitude. So in order to figure this out, we need to figure out the magnitude, in this case r, which is the square root of 1 squared plus negative 8 squared. I get the square root of 65. And so what I get is 1 over 65 in my I direction and negative 8 over 65 my j direction. All right, that wraps up what I wanted to take a look at for the free response questions. But I do want to take also a brief look at what we had going on with the multiple choice as well. Dividing line here. So number 1 on the multiple choice. We are asked to find, given a particular function, the average rate of change from -2 to 2. So our function here, f of x, is equal to 2x squared plus 4x minus 2. And we want the average rate of change on -2, 2. Now, the thing that's really hard about this, or the thing that you have to remember, average rate of change is not too tricky. This is just slope. But what's hard about this is the information that I have given you. This and this are x1 and x2. You don't know the y values yet. You need to find those. So I'm giving you the starting x value and the ending x value, and what you need are to find the starting y value and the ending y value. In this case, y1 is equal to f of x1, which is 2 times -2 squared is going to be 8. 4 times -2 is -8 minus 2. I get a starting y value of -2. And my y2, which is f of positive 2, is going to be 8 plus 8 minus 2. I get 14. This is slope. And so this is y2 minus y1 over x2 minus x1, 16 over 4, gives me an average rate of change of 4. All right. 2 is important just as far as like this is the probably most frequently asked question that I saw on the practice materials for the SDC. So be able to do this. Like the expectation to be able to do this, I think is kind of implicit within every single problem that we've worked so far. But I will reiterate again, you need to know how to do this. This is super, super important. And if you're feeling shaky on your unit circle, I need you to stop feeling shaky on your unit circle. This is like, we're past the point where that is an okay place to be. So this is cosine of -13 pi over 3. Now the problem with this, and what makes this a little bit tricky, is that this is not as it stands a unit circle angle. But we have already seen the way we deal with this. If we add or subtract 2 pi over and over and over again, then we're going to find a coterminal angle. Now, what I will say is that a lot of people were correct in doing that on the last test. They recognized, oh, I need to add or subtract 2 pi. Awesome. But they really, really, really struggled with the fact that when you have a big negative number and you are adding a smaller positive number, that the result will be negative. They did not do a very good job of keeping track of positives and negatives. Some people did, and that was awesome. I had some people use even and odd properties, which was super cool. Loved to see that. That made me very happy. But most people lost track of the negative. So we have to do this very, very, very deliberately. Otherwise, we could mess up. In this case, adding 2 pi, so negative 13 pi over 3 plus 2 pi, which I'm going to write as 6 pi over 3, gives me negative 7 pi over 3, which is still not something I recognize, and it's still negative. So I'm going to add another 6 pi over 3, which is going to give me a negative pi over 3, which feels like I recognize it. And maybe you do. If you know what quadrant that's in, then you can go ahead and answer. But it's not it's not quadrant 1. If you're looking at that and you're thinking quadrant 1, then you are not done yet. You need to keep going. And we need to keep going until we see a positive angle that we recognize, which is going to be next at 5 pi over 3. This right here is a quadrant 4 angle. Cosine of a pi over 3 angle is going to be smaller, so it's going to be 1/2. We know cosine is positive in quadrant 4, and so this is going to be positive 1/2. Okay. Bit of a longer problem here. Radioactive element carbon-14 has a half-life of 5,715 years. If a sample of leaf-trapped in volcanic rock is found to have 37% of its original carbon-14 remaining, we need to determine its age. A couple of ways that we could approach this. For half-life, we know that this is saying, so our general kind of exponential decay, a of t being equal to a sub 0 times e to the rt. Because this is half-life, half of our initial amount will be left. You could pick a random initial amount if you wanted it to be like 100, then go for it. It's not a bad idea. So let's just, for the sake of making things easy, let's just say that a sub 0 is equal to 100. If the half-life has passed, that means I will have 50 of my stuff left behind. And it will have taken 5,715 years for 50 of my stuff to be left behind. Dividing both sides by 100, I get that 1/2, by the way, it wouldn't have mattered what you picked, you're always going to get 1/2 here, is equal to e to the r times 5,715. And rewriting this as a logarithm, I get that the ln of 1/2 is equal to r times 5,715. Solving for r is the ln of 1/2 over 5,715. So we can fill out our equation here. Let's just go ahead and say a of t is equal to, I'm going to leave 100 just to make my life easy. Again, it's nowhere in the problem. It's you pick a value and it doesn't matter what you pick, times e to the ln of 1/2 for 5715 times t. In this case, we're solving for t, specifically when we have 37% of the amount of stuff left behind. If we start at 100, that means we will have 37 left behind. See how convenient it is to pick 100. E to the ln of 1/2 over 5715 times t. I get 0.37 is equal to e to the ln of 1/2 over 5715 times t, and rewriting as a logarithm, ln of 0.37 is equal to ln of 1/2 for 5715 times t. Solving for t, multiplying by the reciprocal, I get that t is 5715 to the ln of 0.37 over ln of 1/2. All right. Let's take a look at number 4 here then. This is cosine inverse of sine of 3 pi over 4. Okay. Well, let's start with what sine of 3 pi over 4 is. This is a quadrant 2 angle. Sine of 3 pi over 4, we know sine is positive in quadrant 2. So what we're really asking here is what is cosine inverse of root 2 over 2? The thing to know about cosine inverse is that this will either be quadrant 1 if it's positive, or quadrant 2 if negative, if the inside is negative. Because here the inside is positive, this must be quadrant 1. In particular, this is going to be pi over 4. Right. And then lastly, transformations. We're trying to do to the right by 4 and down by 5. Just remember that to the right, you do the opposite, and down, you do what you would expect. All right, hopefully you found this helpful. If you do have any questions, feel free to reach out. I'm more than happy to take a look. You guys are going to do awesome, and I will see you all tomorrow for the test. Best of luck with your studying, and take care.